Yeah, thank you. So we are doing basically numerical simulations um, to check if there could be signs of extra dimensions in neutron stars. Um, and so basically, this is the outline of my talk. I'm going to start with a small motivation and then how we model stars, what are extra dimensions, what is the model that we are using, and if there could be multiple extra dimensions, how that could be written down. There's going to be some fun facts and eventually results. And so here is the motivation. First of all, there are many theories which try to solve different problems of modern physics. One is how to merge general relativity with quantum mechanics, for example. The other is the hierarchy problem. Why is general relativity, why is gravity much weaker force than all other forces that we know? What is dark matter? What is dark energy? How this could be described? And there are multiple models which try to solve these problems, and some of them have extra space-time dimensions in them. So basically, we are studying one of those, very simple one, which has only one extra dimension, but I'm going to talk about that a bit later in the talk. And the question is how we can test such theories. And our answer here is that maybe we can see them in neutron stars. And so why neutron stars? These are objects which are very small. They are like the size of Budapest, for example, like larger cities. They are very heavy objects. So this means that they are very dense and also cold, meaning that it's cold in a sense that we have this QCD phase diagram on which we have different extreme conditions of matter. And neutron stars are somewhere on the bottom right, not as high up as in temperature as like heavy ion collisions would be, which can be considered hot. And neutron stars are still very hot in an everyday sense, but this is a regime which, because of the density and because of this relatively cold environment, cannot be produced on Earth or in laboratories. So they can have implications to matter which couldn't be otherwise tested on Earth. So that's why many people are studying neutron stars to get some more knowledge on how matter is behaving in these environments. But to have some sort of information coming out of these stars, we need to model them. We have measurements of neutron stars, like mostly they are measuring their mass and radius. These measurements become more and more precise, and you can also measure other aspects like different electromagnetic radiation coming from them, or this tidal deformability, which comes up in neutron star collisions. But so far, we don't have too many neutron star collisions with a lot of data. And what we are concentrating in our work is on the maximal mass of neutron stars, which can be measured pretty precisely, and it is also quite easy to simulate numerically. And what we can see on the right is this so-called mass radius diagram. There is mass of the neutron star on the left axis and the radius on the bottom. And these curves were produced from different equations of state. And these are basically parameterized by one of each curve is coming from a different theoretical model, and then the parameter of each curve is the central energy density of the star. And what we are interested in how high these curves go, because it constrains quite what kind of equation of state is in it, because there should be an upper limit because of, it would collapse into a black hole if it goes too high up or something similar. And we know that the most massive neutron stars should be around 2.2 solar masses or something like that. So how do we actually numerically build stars, we basically use very simple equations. This is just the classical version. So we look at how pressure changes as a function of radius. So basically pressure balances gravity. That's what we are looking at. And we build a star up layer by layer from the inside. And this is the general the relativistic version of the same thing that I've just shown. So here the first term in this equation, the Tolman-Oppenheimer-Volkoff equation, is just the same as the Newtonian one. And then there are some relativistic corrections. So this is basically the same. It tells how pressure changes as we go in the radius. And then one can integrate this. And after the pressure drops below a certain value, then we can say that this is the edge of the star and this is how large it is and this is what mass it has. And so this is one of the boundary conditions. What is the pressure on the surface of the star? And then the other is just the central energy density of the star. And we need one more thing, which is the equation of state, because as we can see, there is pressure on the left and then there is energy density, this epsilon on the right. And we need an equation which connects these two, and that is basically going to be the equation of state. And that is where extra dimensions come into the picture. Oh, no, not yet. Okay. So yeah, this is basically about the integration and some numerics. So we integrate from the inside out. And this graph shows how the pressure changes as we go from the center of the star towards the outside. And you can see that it drops. And then when it drops below a certain value, we just stop the integration. And this part numerically is quite easy. We use an explicit Runge-Kutta method, and it's important that we use an adaptive step size, because otherwise it would be quite slow, and to use the right units. But otherwise, it's not a difficult thing to do numerically. And then we get these MR curves, and on this MR curve, mass radius curve, basically every point that you can steer, every star corresponds to a certain neutron star within a certain model with a certain equation of state, but starting from a different energy density. So basically a different size star within the same model. And now comes the extra dimensional part. So what we use is the Kaluza-Klein theory. This is the first extra dimensional theory that was ever created. This adds one extra dimension to space-time, so we will have one more dimension, spatial dimension, which is a compact, a small one, curled up in a circle. And this basically gives a quantum mechanical interpretation to the theory, because the saying is that we don't see this dimension in usual circumstances because it's just very small. And this is also a base of a lot of other theories, extra dimensional theories and scalar tensor theories of gravity. And many build on this, and we use this as an effective model of other extra dimensional theories, and we choose this for its simplicity. And here is the metric tensor of this model. So basically, we have the usual gravitational metric, and this 4-dimensional one in the top left corner, and we could add electromagnetism, this A4 vector. We neglect this so far, and what also arises in this theory, because it was originally was made to unify electromagnetism with gravity. But when people do this and put everything into a 5-dimensional metric tensor, then there's going to be one more term, which can be associated with a scalar field, and that could be interpreted in different ways. It's like it could be an extra mediator of gravity, for example. But in these calculations, we set this to unity, and we also neglected electromagnetism so far. But what we have is a modified dispersion relation, because if we allow particles to move also in this extra dimension, then as you can see on this little cartoon, it's like it can be imagined as a circle, if a particle is moving around it, then it cannot have any momentum. It obeys a periodic boundary condition. So this is going to follow certain, it will have certain energy levels, which is described by these some excited states, and I also have a graph of that. So basically, the energy of the particle is going to be just the free momentum, the momentum in the fifth dimension and its mass. And the fifth dimensional momentum can be described as this nx over rc. Nx is just which excitation is it, and rc is the size of the extra dimension. So it's producing energy levels depending on the size of the extra dimension, as it can be seen on the right in this so-called Karuza-Klein radar. And if we set the size of the extra dimension to a certain value, then it can produce some hadronic-like spectrum. So for example, in the middle row, the first excitation will be the lambda particle if the base is the neutron. Of course, this doesn't produce like a proper hadronic spectrum, but if one considers also other extra dimensions, not just one or some combination of different extra dimension sizes, then this could be made more accurate, but so far we stayed with just one. And here's the equation of state. And so this is basically where the extra dimensions come into place. The hydrostatic equations are fully described by general relativity in this simple case where we only have, where the scalar field is set to 1, but the equation of state has extra dimension in it. Basically, in this summation, because we sum over all the different energy levels as if they were particles with different mass. So if we have a particle that is moving in the fifth dimension, then it could be thought of as from a three-dimensional point of view, as if particles had different mass, simply. We also had the repulsive potential. This is needed because in a very dense regime where neutron stars are, basically, you need to have something that mimics the strong force. And the thermodynamical variables can be calculated from this, the pressure, the energy density, and they are going to get some interaction term based on this very simple linear potential, which is linear in the Borel number density n, and psi is just a parameter. It's a parameter of the theory, and this is going to cause actually to calculate this equation of state is not so simple numerically, because as you can see on the right, the number density is going to depend on this potential through mu, which is the chemical potential. So this is going to be an optimization problem, and especially when we have multiple extra dimensions. So this can be quite complicated to calculate, and this takes some time. For that reason, when we do the calculations of the equation of state, we basically save the data and then use an approximation of this data to do the further calculations. So for example, if you have multiple extra dimensions, this problem becomes much more complicated, because even if we use a very simple model, when we have all the extra dimensions have the same size, and we even don't let the system to have any type of excitation, so we maximize it somehow, this becomes quite complicated mathematically, because there are going to be a lot of combinations. And here is the fun fact that this is actually equivalent to this game, this so-called Connect 4 mathematically. This is quite complicated. So if you want to know how many combinations are there in this game, then it's a very difficult program, and it cannot be solved explicitly. You have to do some numerical calculations, but luckily, we don't have to solve that. So this would, for us, this would say what is this G factor, the multiplicity of the states, but we don't really need that because it's enough just to calculate what kind of states there are combinatorically, and then we don't have to solve this program. But it is going to be quite important in this optimization when we want to get what is the number density for a certain chemical potential. And that, in this case, with multiple extra dimensions and multiple excitation, is going to be quite difficult to solve. And so here are some equations of state calculated. This is only for one extra dimension. And what you can see is that there are these bands, which basically, these are spanned by different extra dimension sizes. So this is the pressure as a function of number density. And there are these gray curves, which are just equations of state taken from other publications. And basically we put them there to see that our equations of state are sort of similar, so they are not very far-fetched. And what you can see, the different colors correspond to different interaction strengths. So the green one is where there is no interaction. That is not very physical because this cannot even produce large stars. But the effect of the extra dimension is the largest there. If we have a more realistic equation of state with some repulsive interaction built in, then the size of the effect of the extra dimension is going to be smaller, but it still has some effect. And this is again just the effect of extra dimensions, but the 4 different graphs show different excitation numbers. So we maximize the excitation number at somewhere. In most of the calculations, it was 10, because that seemed like a nice middle ground. It's also better to calculate numerically. It takes less time, and you also don't expect to have very high excitations. They wouldn't even appear in neutron stars because there is just not enough energy present. And basically, we calculated the MR diagrams, solving the Tolman-Oppenheimer-Volkoff equation for hydrostatic equilibrium, and using these equations of state, which include also these extra dimensional effects. And we can see that if we have a correct interaction strength psi, then it is possible to produce curves which produce realistic stars. And there are also some measurements plotted here for certain pulsars, both for mass and radius, and we can produce. What we really wanted to check is, well, there's a quite large parameter space for this theory. So what we did is we plotted the maximal masses of neutron stars as a function of the size of the extra dimensions. So what we are trying to see here is for what size of extra dimension there is any effect in neutron stars. And so on the right side, in the right graph, basically there is each point on those curves comes from one of the curves on the left. So for each point on the right, we had to calculate one of these curves on the left and then take their maximum. So this was numerically quite a lot of calculations. And basically, what we are seeing is that extra dimensions have an effect in our model in neutron stars, for neutron stars observables, if they are larger than about 0.2 Fermi. Because if they are smaller than that, then it would mean that the energy needed to excite even the first energy level would be too high and is just not present in neutron stars. So if we have extra dimensions and their size is larger than 0.2 Fermi, then it should be possible to see them in neutron stars observations if they are precise enough. And also, this is a toy model basically, but if the model is a bit more refined, then comparing it to measurements could give some constraints on extra dimensions. So we also did a comparison to other theories, what they are theories and measurements, basically what they are predicting, what constraints they are giving for extra dimensions, and this differs based on the theory and based on the type of measurement that they were doing. There are some numbers here, some of them coming from gravitational waves, or just theoretical calculations, or yeah, given from even from solar system physics. And we plotted them here to make them more more visible, more didactic. And so the green region is basically what we got from neutron star simulations, that this is the region on the bottom, there is the size of the extra dimension. And so the green region is where the extra dimension is larger than 0.2 Fermi. And what you can see here is basically that there's a quite large overlap with these predictions of other theories. So this could mean that in these theories, the extra dimensions can have effect on neutron star observables, basically. So basically studying neutron stars as a point of view of constraining extra dimensional theories could be a useful thing to do. And as a summary, so there are a lot of new theories that are trying to describe physics, high energy physics, how quantum mechanics and general relativity are related. And many of them are extra dimensional ones. And so we wanted to test extra dimensional theories. For that reason, we used the Karuza-Klein theory as a phenomenological model of these other theories. It's a very simple one with one extra compactified spatial dimension added to spacetime. And there are some observational possibilities. There could be neutron stars, black holes, or heavy ion collisions, for example, or even tabletop experiments exist that test extra dimensions. But what we did here is we wanted to test it in neutron stars, so we simulated neutron stars. And these extra dimensional effects go into the neutron stars through the equation of state, which is modified by these particle excitations in the extra dimension. And what we got is that extra dimensions can have an effect on neutron star observables if their size is larger than about 0.2 Fermi. And in that case, it is possible to get some information on extra dimensional theories. And there are some numerical difficulties listed here. So the integrator of must be chosen carefully, but this is not really a problem. The only problem is that, for example, the last figure that I've shown here is this right one is a bit, you have to calculate a lot of MR diagrams, mass radius diagrams to get this one. But the calculation itself is not, it's not heavy, but you have to do a lot. And the other is the determining the equation of state in the case where there are multiple extra dimensions can be difficult. This is a quite difficult optimization problem. And then, of course, what I haven't mentioned that we have to calculate a lot of MR diagrams, but basically this is a problem that can be parallelized because we are just doing the same calculation again and again and again. So that is not a problematic part in that sense, but rather the optimization. So in summary, we are, yes, this was the summary. So thank you for the attention.
Thank you very much, Anna. Questions? Tamás, please.
If such extra dimensions of 0.2 Fermi radius would really exist, should not it have consequences on all QCD and proton-proton, proton-antiproton cross-section, and so on?
I mean, one of the solutions is that sometimes people just don't let particles move in the extra dimension. So here we wanted this because we wanted to simulate the hadronic spectrum, but of course it doesn't give back the hadronic spectrum in the way as it is, but it rather gives like I don't know, qualitative way of how extra dimensions would affect neutron star observables or the equation of state, if they would make it softer or harder, or how it affects basically. So it's a very rough estimate.
My question, could you go back to the MR diagram? So it was a bit surprising for me that so large effect is there in the. Do you have a qualitative explanation of why it goes up? I mean, the maximal mass.
So the maximal mass, I mean, there are these different colored curves like here, and these are basically set by the interaction strength. So that the effect of the extra dimension is actually not that large. So the extra dimensions effect is more, can be seen more in the right graph, basically. And the interaction strength is something that should be fixed from other calculations, but for here is just a rough parameter, and we set it to about 1,000. If you set it to about 1,000, then it's, yeah.
I just want to point out that elementary particles are affected by your considerations, quarks, and not nuclear. So if you want to alter the structure by extra dimension at high density or however, it really goes into the study of quark matter with extra dimensions, not into nuclear matter and extra dimensions. That's what I would do.
Okay, thank you.
Yeah. There are many of these kinds of models. So this we wanted to have something extraordinary, and to present that it's compatible with the theory. But from course, you cannot really get this. Yeah. Okay. This is very easygoing. I mean, you can. This dimension, it's also easy. I mean, you have more extra parameters for the core, and then you can have.
You have all these wonderful surface explanations of fermions with, and you can turn on and off degrees of freedom. I mean, you can have. So there are lots of opportunities, but they are all at elementary particle level, and you have somehow to mix it with density. If density plays no role, that's excluded by experiment. So it has to be really a consequence of many particles being together, that you actually changing the compactification radius. But you just remember, what you do now can happen in vacuum. And that is excluded by experiment on various, Tamash and other comments. But you have plenty of opportunity to claim that compactification is also matter density dependent, because we have domain wall fermions, for example. And so if you put lots of domain wall particles together, maybe the domain walls stretch and become large. And then, so you have to have density dependent of RC, and that's how you could get what you want.
Thanks for the idea. I think this could be a good point for Anna to do for things. Any further remarks? We are getting tired, so let's stop here, and thanks all the speaker and Anna again.